Okay, so the first thing we're going to go through is just like really some basics. If you guys noticed on your first free response test, you probably saw that there's a different type of questions that are asked on a free response test compared with the multiple choice test. There's a lot of like listing, like on the last test you had list of factors that affect evaporation rates or whatever it was, reaction rates. And so we predict that there will be similar types of questions on this test. It'll be more of a conceptual understanding. So what I want to talk about first is just some of the things that we've hit on in class and just review them, so make sure everyone has them crisp. First thing, strong acids and strong bases. You should know them by now. I just wrote them all out. If you want to go through them, just to make sure you have them. There are 6 strong acids. The strong bases are really easy. It's everything in the first column and calcium down in the second column. So that's just the easiest way to memorize it.
Can I add one thing about that?
Sure.
Don't just be able to recognize them, but be able to like look down at a piece of paper and write every one of them. Okay? Not because if the question is write all the acids, you might be good at recognizing, but have them actually memorized. Like please have them memorized.
Yeah.
He said that the conjugate bases of strong acids are negligible. For H2SO4, does that mean the SO4 ion is a negligible base?
Not in that case, because it's diprotic.
Okay.
Yeah.
Good question.
Any other questions on this, strong acids and bases? Okay, let's go through the different definitions of acids and bases that we've done so far. So let's start with the most simple theory, way of thinking that we've done, the Bronsted-Lowry definition of acids and bases. I would definitely know these and know how to describe one. So if he gave you some kind of problem that's like a proton is transferred, what type of acid is that? Just be able to know. Bronsted-Lowry bases have to do with proton transfers. Acids are proton donors, bases are proton acceptors. Okay? Arrhenius acids and bases. What those do, they're typically in solutions, and an Arrhenius acid will increase the H+ ion concentration in the solution. An Arrhenius base will increase the OH- concentration. So that's basically all you have to know for that. Lewis acids and bases, we've kind of talked more about since we've got into the coordination chemistry. What it has to do with, it has to do with lone pairs on molecules. So some of you may have been wondering, like, how is ammonia a base, you know? Normally our acids have those hydrogen atoms on them, but ammonia, you know, it's got those 3 hydrogens, so you may wonder why it acts as a base. And the reason is when you draw ammonia out, it has these lone pairs right there, okay? So what these lone pairs can do is they can go out and grab a hydrogen off another molecule. So if we have HCl here, what these lone pairs can do is they can go out and grab that hydrogen. So the definition of a Lewis base is something with 3 lone pairs that can go out and grab a hydrogen. They go out and attack stuff. The definition of a Lewis acid is something that is susceptible to a lone pair attack. Okay? So when we've been doing our ligand stuff, we've dealt with like copper and cobalt, those ions with 3+ charge. Those are very easily susceptible to a lone pair attack. So that's what our ligands are doing, is those ligands are using their lone pairs to come on and attach to that metal. So that is the definition of a Lewis acid. Any questions on these definitions? They should be pretty straightforward. Okay? Moving on. Who can explain to me the difference between endpoint and equivalence point? Yeah.
The equivalence point is where there's...
Loud, really loud.
The equivalence point is where the H+ ions are equal to the OH- ions, which makes it well, I guess you could say a neutral compound. But the end point is basically when the pH starts going towards the hydrant.
Yeah. Yeah, so if any of you guys didn't hear him, what the equivalence point is. The equivalence point is when your moles of analyte equal the moles of titrant. So this is at equivalence point. You guys have probably done a lot of BAA tables where you have your analyte, you have the same exact amount of moles of your titrant, and when they equal, you're only left with conjugate, okay? So that's the definition of the equivalence point. When the moles of the analyte and the moles of titrant are equal, and you're only left with the conjugate acid or base. The end point is where the main thing to know is that it's where our pH indicator changes. So if we have, like we did that example in class with the green solution and it changed colors, that's a pH indicator. So when our pH reaches a certain level, if it's going more basic, the end point is when that indicator changes. So the best indicators are the ones that change at the equivalence point. You know, it changes. But in reality, the end point can be anywhere on this steep incline. If you look at a titration graph, our equivalence point is going to be right here in the middle. The end point is just when the pH indicator changes. So that can be like your litmus paper, your methyl red, any kind of pH indicator. Yeah?
So will the equivalence point always be right there in the center of that large incline?
Mm-hmm. Any more questions on this? End point and equivalence point? Yeah?
Said that it would be like it would be neutral when he like.
So it is a neutralization reaction is what we're doing. So if I were to write this out, let's say I have acetic acid. The definition of a neutralization reaction is I'm canceling out what I have. So if I'm doing a titration with acetic acid, I'm going to want to neutralize that with a base. And when I do that, water will always be a product and the conjugate of what you started with. So in this case, it would be acetate.
Yeah, but the pH won't necessarily be 7, right?
No, no. Yep. Any more questions on this? And again, these are types of questions that Dr. Macedoni could just say, name the strong, write all the strong acids, write all the strong bases, write the definition of a Lewis base, write the definition of a Bronsted-Lowry acid. So just make sure you have those crisp and that you can explain each of them. Okay? We're good on here? Yeah.
Quick question. Just like, I know like what a strong like a base is, but when you say like list them all out, technically which ones does it start at for each row? I know calcium down, but then what about the first one?
On the first one, it's lithium to cesium typically. Like the francium, it's so rare and it's really big, it doesn't really work.
So that's the same for RA, right?
So you would go calcium to barium. Yeah.
And I doubt that he would have you write all of the strong bases, but rather like 5 of them.
Write 5, write 6 of them.
8 of them, write 7 of them. You know, so you choose which ones that you want to write.
And remember that your divalent cations are going to have 2 hydroxides attached, okay? Those charges have to equal. So this is a calcium 2+, so it has to have 2 OH-. Yeah, Courtney?
So you said that H2SO4, the conjugate or the conjugate base might not be negligible because the H2 would have the same number of calcium hydroxide.
It doesn't really work the same like that with bases. We typically just think about it with acids if they're diprotic. So you know, like if we were to put this in water, the main thing to know is that it would produce 2 hydroxide ions. So if you were going to calculate the pH, you'd have to take that into account in your ice table that it's going to produce 2 hydroxides instead of just 1. Any more questions on this before I hand it over to Greg? Okay.
So if I have just a couple comments to make because Corbin did a really good job at like just pointing out a few of the things that are common mistakes. One of them being the fact that calcium hydroxide, there are 2 hydroxide ions. Don't forget to write that. The other one being a little bit about endpoint and equivalence point. So just make sure again that you know the true definition. And he said that the endpoint is when you have the pH indicator change, right? It's very important that that is in your idea of the definition of an endpoint. Not just when like, oh, we get towards the pH of the base, but rather the actual indicator that tells us when we're at that end, okay? And then another student over here, I can't remember, brought up a good point about when we hit equivalence point, well, if we were titrating a strong acid with a strong base, it was you. That would be at 7. That's exactly right. But if we had a weak acid and we titrated it with a strong base, kind of like in a situation like this, at equivalence point, where would I be? Where would my pH be? Above 7 or below 7? Above 7, exactly. Okay, you guys got that down. Okay, good. Let's kind of like transfer over here and talk a little bit about something that I know that Corbin and I were not tested on because we didn't even talk about it in the class. But he talked about it enough in your guys' lectures that I feel like it could potentially be something on your free response exam that we didn't see. But that's more specifics about the autoionization of water, right? Understanding exactly what that means. Now, it's a pretty simple concept. I have the equation written here. But what the idea is that water, H2O, is not just H2O in any sort of solution, but rather there is some ionization going on where a water molecule reacts with another water molecule, and you only form, hydronium and hydroxide. There are a couple really important things to understand. I know we've hit this several times. We'll go over it briefly, really quickly. Whatever concentration I have in pure water of these ions, the concentration of both, they will equal each other. And that makes sense because when one of these waters reacts with another, it wouldn't produce two of these and one of these, but rather one of them gains the proton and becomes this, the other one loses it. So that's why these concentrations always are the same in the autoionization of water. So I write this question here, why is this important to understand? Besides just knowing, yeah, that happens, that's great. But why is it important for you guys to really understand this process? You could tell me why? Hopefully someone. Yeah, and then we'll have you say something as well.
So when the concentration of like an acid gets really small, you can maybe make a mistake and say that it's going to be neutral or like basic.
Exactly.
But because you understand the autoionization of water, you'll know to do the equation and figure out what the pH really is.
Exactly. What you said is perfect. And we'll see, is that what you were going to say? Okay. So that was really well said. What he said was, when we add a little baby amount of acid, anytime you take the negative log of anything that is raised to 10 to the minus 7 or smaller, you're going to get a pH of 7 or basic. If I say that I add 1 times 10 to the negative 8 molar of HCl, if I take negative log of 1 times 10 to the negative 8, thinking that'll be my pH, I get 8 as my pH, and that's basic. But I added a little bit of acid, so it doesn't make sense. That's because I need to factor in the fact that the autoionization of water is occurring. So one more time to conceptually understand this. When any time I add acid to water, at any time, you got to understand there are technically two reactions occurring. One of them is with the acid and water to produce this guy right here. But another reaction is with water and water with itself, right, to produce a little bit of this. So we have two sources or two reactions that are giving us a little bit of hydronium. Now, it only is a factor, like he said, when we add a little tiny bit of acid. Because when we add just a little bit of acid, I still need to factor in the amount that water makes of this. What is it normally when there's no acid in there? What's the concentration of these two? 1 times 10 to the negative 7. So my Kw for water, the autoionization of water, is 1 times 10 to the negative 14. That's just really important to understand. But what happens when I add a lot of acid, I don't have to worry about this anymore because you guys would understand this. What principle that we learned in chemistry about equilibrium, right, tells me that when I add a ton of acid, I no longer need to worry about this equation or this reaction in water. The Chatelier's principle, perfect. That means that the Chatelier's principle is this equilibrium shift. If I had a bunch of acid to water, I increase this concentration by a ton. Where will my equilibrium shift? It goes back this way, which means that these two stop reacting with themselves and just worry about reacting with the acid that's present, right? So that's why sometimes I worry about this when it's a small amount, and sometimes I don't, okay? If you are adding anything of an acid that is 1 times 10 to the negative 7 or smaller, think about this. And the final equation I can write on the board, just that you guys can put this in your notes and know that this is the equation you will use to get the overall pH if you had a small amount of acid with a little bit of water here, would be this. Kw is equal to the concentration of your acid, right? And I put a line right here, meaning this is the amount that's coming from the acid that I added in water. So I could make up an amount right now. I'll make it up. We added 1 times 10 to the negative 8 molar of hydrochloric acid, a strong acid. So the H plus or hydronium that's coming from the acid will be 1 times 10 to the negative 8. X is the amount that's coming from my water, but I don't know that amount, times the same times hydroxide here, and I know that they're always equal to each other, so if this is X for the acid that comes from water, then this is X as well. That'll always equal Kw. But once I solve for X, I can plug X back into just this concentration. That is the total concentration of the solution. I take the negative log of that, I get my answer. So keep this equation in mind just in case, okay? So, who had a question?
I was just going to ask if that's the concentration of the acid that you said.
This is the concentration of the acid, this little part right here, 1 times 10 to the negative 8, that I added. But the overall is my overall amount of hydronium in my solution, that's including how much of hydronium water is giving me, plus the amount that my acid gave me. Notice, I only do this when these numbers are really small.
So that'll be the total pH.
This will give me the total H plus concentration in the solution, and I can get my pH from that.
So so that 1
times 10 to the negative 8, that's a value that you got from already doing like other.
That's a value I got because what I explained was just that we added HCl and we added 1 times 10 to the negative 8 molar HCl. Like I added that much acid into a little bit of water. So since this is strong, I get the same amount of H plus. Some of this overall amount of H plus in my solution comes directly from this, and some of it comes from this equation.
the 2 X's are just the hydronium and hydroxide.
The 2 X's are hydronium and hydroxide. Jim?
If we're not adding HCl but a strong base, we just do the same thing, but just
Opposite, exactly. Okay, cool. All right. So let's get into our next favorite thing. Now we got the autoionization of water almost covered.
That's just with small amounts of acid, right?
With very small amounts.
Or can it be with small amounts of base?
Or base, right. Very small amounts of either, right? You would just switch whatever one you're solving. You'd get a POH for one, but you would get a pH for the other. So just make sure you know that. Okay, salts. We've done this a bunch. You guys kind of hate them and love them at the same time. I feel like this is one of those things that we talked about earlier where it's like, you like understand it really well, you go in to take the test, then you maybe see your score, and this might be one of those areas that maybe you glitched or maybe something tripped you up. Because salts, some of them are easy, some of them are not as easy. So this is what we're going to do. You guys are going to look at these. Honestly, you should be at the point now where you can look at almost all of those that are listed and know immediately if it's going to be an acidic or basic solution, right? Maybe 1 or 2 of them you'd have to look at a little bit longer, maybe do some math. I wrote some KAs that might be of interest to you down here to solve for something, right? But this should be a question you can answer in probably a minute, all of them. And what I'm going to do, give you a minute, you're going to do your very best, get if these would be neutral, basic, or acidic, and then we're going to go through and we're going to have everyone, we're going to answer them together, okay? So you got a minute to solve this.
Are all the K's and KA or is there a KB in there?
Maybe put it, can you put it up a little higher? Like put this one in, even put this one up a little higher. We'll raise it just a little. Yeah, both of them. Keep going. Can you guys all see this now? These are all KAs.
It's just written.
Okay. Yes, they're all KAs. Yep, sorry. Yeah, they're all KAs. Okay, we're coming up on 15 seconds. Gotta hear that sword coming out of the sheet, you know. The calculator. Let's get it. It's a very sweet sound.
CSF.
This is CSF on the top. Cesium fluoride, ammonium iodide, cobalt tetrachloride, and ammonium fluoride. Okay, let's do it. This is how we're going to do this. I'm going to start with the top one. And what we're going to do is, if you think that it is basic, you're going to put a 1 behind your head like this. Right? You're going to put a 1. If you think it is basic, if you think it is acidic, you're going to put a 2. If you think it is neutral, you're going to put a full hand. A full hand is neutral, acidic is a 2, and a basic is a 1. And you're going to do this because this is something that Dr. Macedoni talked about doing. And I'll tell you why it's important. Oftentimes when we do these reviews, you guys become master observers. You can watch and observe really well. But sometimes having to maybe present an answer is just enough anxiety or annoying just enough that it helps you remember it better, I promise. I don't love doing this, but there is some benefits to having to do something weird like this, okay? So right now, everybody, put behind your head what you think is. 1 is basic, 2 is acidic, 5 is neutral.
Wait, what is this again?
1 is basic, 2 is acidic, 5 is neutral. Okay, so those of you in the back can see forward. You should have a 1 behind your head, right? And most of you did. That's great. I actually, at the end, I started to see only 1s. That's perfect. This would be basic. Basic, why? Because of the fluoride ion. Okay, number 2.
One is basic, 2 is acidic.
1 is basic, 2 is acidic, 5 is neutral. You should have a 2 behind your head. Good job. Most of you did, almost all of you did. This would become base, or make it acidic, because the iodide is the conjugate base of a strong acid. It's negligible, but ammonium is the conjugate acid of a weak base. It would make it acidic. Good job. Okay, cobalt tetrachloride. Go. Where does cobalt come up?
1 is basic, 2 is acidic.
Let's see what we have. Now, 1 is basic, 2 is acidic. You should have a 2. A little bit harder. You should have a 2. Okay? Because cobalt is the conjugate acid of a weak base, right?
It's a Lewis acid.
It's a Lewis acid, technically, right? That's what we're looking for. That was a little bit trickier. The last one, ammonium fluoride. Take a look at this. 1 is basic, 2 is acidic. What do we got? We're all over the board. I'm seeing neutrals. I'm seeing other things. You should have a 2 for acidic. This is harder. We're going to talk about why. Let's talk about why. The reason this is acidic, you guys notice when we break this salt up, we get conjugates of weak things across the board. We get ammonium is the conjugate acid of a weak base. We also get fluorine or fluoride ion, which is the conjugate base of a weak acid. What happens when both pieces of my salt could do something? How do I solve that now? I have to compare my Kas, which is why I gave you values, right? Immediately, I know the Ka, or how strong ammonium is, this piece of it. 5.6 times 10 to the negative 10. But I need to figure out what is the Kb, the fluoride ion. And right here, I have what the Ka of hydrofluoric acid is. And you don't even have to really do math. You could look at this and say, well, 6.8 times 10 to the negative 4, they all equal 1 times 10 to the negative 14, right? So I know that if I do the math, the Kb will be something times 10 to the negative 11, right? Which I know is a smaller number than something times 10 to the negative 10. You really didn't have to do math. You could just have looked at it. You know that the acid wins out. It's got a bigger Ka. It's acidic, okay? So that's a good problem. It's something like that to keep in mind. Be able to directly say acidic, neutral, or basic for however many salts he would like to give you, okay?
So if he doesn't give us Ka values,
There's no way to do it.
okay.
He's never asked you to memorize them. So if he doesn't give you a Ka, feel comfortable that it is solvable without that. And so whether he gives you hints about it, whatever, but it is solvable without real numbers. Andrew.
So
Loud.
So when you have a Ka and a Kb, how then do you find out if it's acidic or basic?
So all you do, I get the Ka, and I compare it to the Kb. Whatever one is bigger, in this case the Ka was bigger, it's acidic. But if it had been the opposite way, it would be basic. Just look at the larger number of the K, okay? Okay. You want to raise it? Oh. Yep, the fluoride here is the conjugate base of this weak acid. And I gave you Ka. You had to solve for Kb. Okay? This is an important one to know how to do. And you guys all did really well with the numbers and putting them above your head. So it looks like almost all of you have this down, besides maybe a couple of shakies with like the Lewis acid and base. Okay? So, Graphs. We're moving on. Graphs. This is important. Right now, all of you should have a piece of paper out in front of you or something to take notes. If you don't, hurry, pull it out. Just get ready to write a couple things. What I want you guys to draw is the graph. Focus on this, right? The graph of a titration of an acid, right? Titration of a weak acid, right? That's it. Draw the graph of a titration of a weak acid.
Strong base.
It's always
If it's a weak acid, it could only be a strong base. Yeah. Okay. I am. Okay. Ready? Ready? Okay. Oh, Corbin's got it, but we're going to redraw it. Okay, we have a weak acid titrating with a strong base. That means my weak acid pH is probably not 1 or 0. It's a little bit above that. As I come about, I keep adding my strong base and get to the point where it really increases and approaches the pH of the strong base. My equivalence point would be here. So it's something like this. Okay? It's as simple as that.
So you can never titrate a weak with a weak.
A weak with a weak you can, but it's like a really mathematical nightmare. I don't think we've really ever talked about it, and if he ever did that, I don't know.
I have two quick questions. So one is, what pH defined as a weak acid? Like, is it above?
So a weak acid is defined as just about anything with a pKa that is above -2.
Okay, and then also, what would that graph look like if it was a weak analyte?
This is what the graph would look like. We have a weak analyte, and we're titrating it with our titrate. What I'm showing here, like the pH is 0 here, 1, 2, 3. We might have a pH around 2 or 3 for my weak acid, but strong acids are going to give me a pH almost starting at 0 or even negative sometimes. Really strong ones. It depends on the concentration. But the important part was not necessarily knowing this part. We're going to get to why this is important. Now, you need to draw on your piece of paper, draw a graph of a titration of a diprotic acid. Diprotic acid. Ready? Diprotic acid. So I'm going to start out. My only diprotic acid I really know is strong, so I guess I'll start out more towards the corner. I come here, I come up a little bit, and I go, but it's diprotic. There's another one. You should have got that. Okay? There's equivalence points for both of these parts. Okay? Just be able to draw the graph. Okay? Yeah, that's.
Does the height of those curves, does that matter at all? Or?
The height of the curve doesn't matter as much as just knowing that you put two curves. Okay? Question in the corner over here?
Yeah. On that graph, at what point do you think the pH would be 7? To sort of get a reference.
It depends on the acid completely. Yeah. So the importance here is not knowing all the specifics, but knowing that it would look like this. Okay? Last one. Everybody start drawing a triprotic. Triprotic. Ready? You guys got it down? Okay. Triprotic acid. All these are acids. Yeah. Thanks. Okay. That's what it would look like. Okay? So there would be 3 humps here, or 3 straight areas where you have only conjugate base. Just be able to recognize and draw for any of those. We don't really go beyond triprotic, but be able to draw that, okay? And the last thing, Corbin and I together, we're going to answer really quick. Titration problems, titration questions. Briefly.
I just had a question on the graph part.
Yeah.
What you draw the difference between a strong acid and a weak acid that's being titrated?
Yeah. So a strong acid is something, the only thing that's going to change is that my pH at the beginning will just be lower.
Okay. So like
But,
if you're not given the pH at all, like you're showing.
if you're not given specifics, if it just says draw of a triprotic acid, that's all you know. As long as it looks like this, that's what they want to know. Versus where did you start, where did you end? Don't worry about, but if it's specific, like it's a weak acid, just make sure you're not at 0. But you can argue your case. You can say, well, some weak acids are pH of 2. You know, you can argue your case. The most important is understanding this space.
So like,
I've noticed with some of the, like when it's a weak acid in the base, at the very initial point, it will have a spike in pH. It'll either go down really quickly or up really quickly because there's not a lot of dissociation in your weak acid. So there's not a lot of like the H's binding to OH's to make water. So it ends up like lowering the pH really quickly or raising the pH really quickly.
On these sections right here?
No, just like at the very initial.
Oh, right here? It spikes when it goes like that. Anything like that, any of those little details,
if you guys have more questions about these graphs, look at Dr. Macedoni's slides. In the lecture, he had a bunch of examples on there. So we just drew a couple, but if you still have questions on it, look at the slides, because I know he did like 4 or 5 on there, on his own slides.
So let's get to titration questions so we can get to KSP stuff and answer a couple more really good questions or things that are going to be important. Titration questions. You guys should have this pretty good. Is there a specific one you're really confused about that doesn't entail doing an entire problem? No? Okay. I didn't think there would be.
Okay, so let's just go over some quick, we did this in our first review for titrations, just the kind of brief, synopsis on, if that's even a word, of the titrations, when you do what. I know a lot of people are confused, like, well, when do I use the Henderson-Hasselbalch? When do I have to do the BAA and then the ice? So just write this down in your notes. Before equivalence point is Henderson-Hasselbalch. Because the definition before equivalence point, you're going to use up all your titrant. You're going to still have some analyte left, and you're going to have conjugate left. Okay? So any situation where you have only analyte and its conjugate left, you can do the Henderson-Hasselbalch. That's the only time you can do it. At equivalence, yeah.
But we also use the BAA table for that, don't we? In order to
Yeah, you do the BAA table and then the Henderson-Hasselbalch. At equivalence point, you're going to do a BAA and then an ice. Don't forget, ice is always in concentrations. So at the end of your BAA table, make sure you convert those to molarities by dividing by the total volume. Third, after the equivalence point, you're going to have leftover strong component. And so what you can do most of the time is just get that into concentration. If you're titrating with a strong base, you're going to have leftover OH concentration. Get the concentration of that, and then just get the pH straight from there. That's typically what it's going to be. A more thorough way to do it would be to run an ice table, again with the conjugate that's left. But all the examples that I've done, it's really not going to change the pH much, just so you know. Yeah, any more questions on titrations?
No, I was going to ask about buffers.
Buffers, okay.
What makes a good or a bad buffer? Because that was on the last test and I had no idea.
You want to answer?
Yeah, sure. What makes a good or bad buffer? This is a good question because you'll get asked this all the time. So a good buffer is one that has equal amounts of acid and its conjugate base, equal amounts of moles of that, right? That makes the most ideal buffer because a buffer is buffering against a basic solution and an acidic solution. So if I have a ton more conjugate base, that might be better or ideal for an acid being added, but not if I add a base. I'm already a little bit basic. So a most ideal buffer is equal amounts. Yeah.
Is it better if they're equal amounts but the molarity is higher of each?
So yeah, the more I have of equal amounts is even more ideal, right? So there becomes a gray area of what if it's not equal but there's a lot versus a very small amount but it's equal. Those are gray areas. That is very like case specific. So just know the generals.
The main thing to know is something with its conjugate equal amounts.
Yep.
Okay, moving on. Okay, we're going to do this problem together. This is a KSP problem. And your question is, what is the molar solubility of silver iodide? And then I want you to calculate the solubility. What's the difference between molar solubility and solubility? Yes. Molar solubility is moles per liter. Solubility is grams per liter. So, the first thing I'm going to do if I encounter a KSP problem with a salt is I'm just going to, like normal with the salt, what are the ions? Okay? So AgI is going to dissociate into Ag plus and I minus.
Just put the AG, finish first AG.
Oh, sorry. Okay? And then we just do a normalized table. And on these questions, he might say like, the silver, you have 20.22 moles of silver iodide dissolved in 35 milliliters of water. He's just trying to confuse you there. All you need to know is you have enough here to for it to be soluble. They gave you enough moles of silver iodide for it to actually break up into its ions. And that's why we always just say there's excess here. And you just never have to worry about it. And you could also figure that out because it's a solid. We never include solids in our K expressions. So, what's my initial concentration of both of these? 0, because I'm adding it in water. So it's just plus x, x, x. So then, I move over, set this equal to my KSP. So my KSP is 8.5 times 10 to the negative 17. And that's going to equal x squared. When you solve for x, it should be 9.22 times 10 to the negative 9. Now, what solubility is this?
Molar.
Molar solubility. Whenever you solve for an x, that's your molar solubility. Okay, part 2 of the question. Yeah?
And then is that in moles per liter?
That's in moles per liter, yeah. That's what we're going to do next. Okay, so how am I going to convert this, my molar solubility, into solubility? Times by the molar mass, right. So I have 9.22 times 10 to the negative 9 moles per liter. This is just a very simple dimensional analysis. I want it in grams, so I want to cancel out my moles, okay? And there is 234.7 grams in 1 mole of silver iodide. Okay? And when you get that, you should get 2.16 times 10 to the negative 6 grams per liter. So this is fairly straightforward. One thing to watch out for is if he gives you a salt where you're going to get like, say if this was CaI2, I would produce 2 iodides, and then I'd have to calculate that in here. And so it's not just going to be easy like this, x squared, it'd be 4x cubed.
So if we're doing a KSP, will the salt always be in excess?
Uh-huh. Yeah, they'll always give you enough for it to be soluble, so you just never worry about it. Yeah?
Will they ever give us a situation where it's like, this is how much, I don't know, iodide you have, find out the original concentrate, or the original amount of salt that is needed?
Yeah. So what I would do if I was you guys is, I think a lot of people when they're taking this class, we do problems, okay? I just had you solve for the solubility. What if, and you need to be thinking about these types of things when you're doing practice problems. What if Dr. Macedoni gave you the solubility and had you solve for the KSP? Could you have done that, okay? Could you have converted this grams per liter into moles per liter, then recognize that that is equal to x squared, multiply those together to get the KSP, okay? You need to be able to work backwards and forwards in this problem. So who said that? That was a really good point. Just be able to recognize, how do I go backwards? If I normally solve it like this, how would I go back? Yeah?
Well, so do we have to have any knowledge of like the solubility rules?
You would, if you don't know solubility rules, I would brush up on it.
Just briefly, yeah.
Just like, I don't know if he's going to give us compounds like outside of soluble.
No, he wouldn't do that.
No, they're all soluble to a degree. That's
Like this silver, like, you guys see how small the KSP this is? This thing is really not that soluble. It is barely, you know, this KSP. And that's one way you can tell if something's more soluble. The higher the KSP, the more soluble it is. Any more questions on this? I have another example with KSTs.
Yeah, let's do the next two because they're really good.
Yeah.
If you said, how much can you add before precipitation, are you just solving for?
That's what we're gonna do.
We're gonna do a problem.
I've got that problem right there. It's a good problem. It's a good one to bring up.
Okay. So now we're going to talk about the common ion effect. And I want to do the same exact problem. But the only difference with this problem is I'm telling you that instead of putting this in water, I'm now putting it in 0.4 molar potassium iodide. Okay? Now, if you just saw this, what would you predict? Would you think my solubility is going to be higher or lower? Lower. Lower, exactly. And it has to come back with Le Chatelier's principle. If I have something and there's no other ion present, it's going to want to drive to that side even harder. But in this case, if I already have some iodide in there, that salt is not going to want to be as soluble. It's not going to want to push to this side as hard because there's already some iodide there. And I'm going to go through it. We'll do all the math to show you that that's valid thinking. Okay? So same thing, AgI. It's going to dissociate into Ag plus and I minus. Ice table. I'm moving quickly. Excess. What's my initial of Ag plus? 0. What's my initial of I minus? 0.4. Plus x, x, 0.4 plus x. So the only difference in this case is I said my initial concentration of iodide is 0.4 molar because this is a soluble salt. It's just going to be the same.